Hello everyone. In previous videos for Laplace transform, we covered these topics. Today, we will be talking about filter design by placement of poles and zero of H of S. And this is basically a client will come to you and says, my sensors is picking up this signal. Can you build a system that will give me a specific output, or it will extract certain data from these inputs? So you have to come up with H of S that will do this job. And there are different ways to design systems and filters, but today we will talk about the poles and zeros placement. Before we start talking about system design, let's review some vectors operations. So let's say we have this vector A minus 2 plus J4. If I plot it, it will be this is minus 2, this is 4. So if I draw this vector, it will be a line from the origin to this point. Now I can express this vector in polar form, which is magnitude, the length of the vectors, and the angle, theta. And the magnitude or the length will be the square root of the real square plus the imaginary square. E to the power of j, now the angle theta. Theta will be tan inverse the imaginary divided by the real. And here you have to be careful, because if you put this in your calculator, it will give you this angle. And it will be minus 63.4. So then theta will be actually 180 minus 63.4, and that will be 116.56. 180, which is the angle of the line, minus this angle. So this will be then square root of 20 EJ. Okay, let's clean up. Let's now do this vector the same way. The real is 3, that's 3. The imaginary is 2, this is 2. So the vector will be this one. And this is vector B. And I can express it in the polar form. So that will be 9 plus 4 E, the imaginary divided by the real. And this will be, so the length here is square root of 13, and the angle here is 33.7 degrees. Now, if I carry out this operation, A minus B, if I plug for A, its value here, and for B, its value here, minus 2 minus 3, I get minus 5, J4 minus J2, I get plus J2. And if I plot this vector, minus 5 is here, and 2 is here. So that will be this vector. Now I can get graphically this vector by connecting the head of this vector B to the head of the vector A. So that will be this one. And this vector is exactly the same as this vector. This started at this point, this started at this point, but they have the same length, the same angle. This is the angle here, and this is the angle. They are exactly the same. So whenever you have two vectors, A minus B, just connect the head of B to the head of A, and that will be the result. Just to show you, let's find the magnitude of this vector. So that will be the square root of 5 squared, that's 25, plus 4, this is square root of 29. Now, if I try to find the length of this vector graphically, I will just create a triangle with the right angle. This length is just 4 minus 2, that's 2. This length here is 3 minus 2 is 5. So then the length of this one will be the square root of this 2 square 4 plus this 5 square 25. And that's the square root of 29. Now, if I do a multiplication, it's much easier to do the multiplication when the vectors are in the polar form. So the multiplication of A times B, it will be the magnitude times the magnitude, so that will be square root of 13 times square root of 20. And I add the angles, this plus this angle. So that will be EJ 1116.56 plus 33.7. And if I do division, then it will be square root of 20, EJ 1116.56 divided by B. And this will be just the square root of 20 over 13, EJ, this angle minus this angle, because when it goes to the numerator, it will be negative. And that's the answer. Okay, that's all you need for system designed by poles and zeros locations. So let's get to the design. To help visualize the effect of the location of poles and zeros on the system behavior or response to a specific frequency, let's do these simple examples. So assume you have an input here with a specific frequency minus 2 plus J4. And we know the output will be the input either amplified, depend on the system response to this frequency. It could be attenuated, it could be amplified, it could be phase shifted. So how can we graphically visualize it? So we can design by placing poles and zeros in certain location to amplify certain frequency and attenuate certain frequencies. So let's say this is the transfer function of a system, and through this example we will see the impact of the poles and zero. So the first step is find out what are the zeros and the poles in the system by factoring out the numerators and denominators. So that will be, when you factor it, s minus 2 and s plus 1, and that will be in the denominator. So this system has two zeros. The first zero is when s equal 2, that will make the numerator 0. The second zero, when s equal minus 1, that will make the numerator 0. Now the poles are the value of s that will make the denominator 0. So for this one, the first pole, when s is minus 5 plus j2. The second is when s minus 5 minus j2. So these are the poles and the zeros of the system. Let's express this transfer function in terms of the poles and the zeros, simples. So then this will be h of s and if I want to find the system response to a specific frequency, let's say to this frequency, then I plug for SSI, that specific frequency. Let's look at first this term, SI minus Z1. If I plot the vector SI, it will be the vector from origin to the point of interest or to the frequency of interest. So that would be this one. Now, if I plot the vector Z1, Z1 is 2. So that would be this one. Now, vector SI minus Z1 will give me a vector that originates as Z1 all the way to SI. So that will be this vector. And let's label it the amplitude R1 and the angle here theta 1. So this quantity will result in this vector. So let's delete this one. We don't need it anymore. How about this one? So let's plot the vector Z2. Z2 will be this one. And this operation will result in a vector originated as Z2 all the way to SI. So that will be this vector. Let's delete this one. We don't need it anymore. And I will call this R2 theta 2. And again, let's plot this vector, the operation of this subtraction. So this will be a vector that originates at the pole. Let's draw the pole, P1. So that will be this vector. And SI minus P1, it will be a vector from P1 to SI. And let's call the length here D1. And now I don't need this anymore. And let's call this angle. Let's change the symbol here. Let's call this not theta, phi1. And this one also phi2. And this we call it theta1. And same thing, this will be a vector from P2, which is this one here, to SI, the point of interest. So that will be here. So let's take this off, we don't need it. And this is the angle. And I will call this D2. So this expression, now it is, this one is just R1 EJ phi1. And this quantity here is just this one, R2 EJ phi2, divided by. This quantity here is just this vector, D1. And same thing for this one is just this vector here. So I can rewrite it as R1 R2 divided by D1 D2 exponential. I add this to angle phi1 plus phi2, and these two angle here will come up negative, minus theta1 plus theta2. And this is the system response to this frequency. It's basically the multiplication of the distance between the zeros and the point of interest divided by D1 times D2, the distance between the poles and the point of interest. This is the magnitude, and this is the phase. So from this equation, if I want to suppress a specific frequency, I need R1 and R2 to be very small. That means I place the zeros close to the frequency that I want to suppress. If I want to enhance a specific frequency, then I need D1 and D2 to be very small. So the whole thing here will be large. And to make D1 and D2 very small, that means I have to put poles close to the frequency that I want to enhance. And that's the idea of poles and zeros placement to design a system. You need to enhance a frequency, put poles close to that frequency. You want to suppress a frequency, put zeros close to this frequency. Now I can find graphically the value of R1 and R2 and D1 and D2 and know what is the gain without even plugging any values for SI and Z1. For example, if I want to know what is the length of R1, let's plot it here. This is R1, this is 2, and this is minus 2, and this is 4. And this is the right angle, triangle. So R1 will be this length, which is 4. Square root of 4 squared is 16 plus this length, which is 4 squared, that's 16. So that is square root of 32. So R1 is square root of 32. If I want to find R2, I draw a right triangle. Now this is R2. So it will be the square root, the length here, which is 4 squared, that's 16, plus this length, which is 1 square, that's 1. So that's the square root of 17. And the same thing, D1 will equal the length of this one, that's 3. So that will be the square root of 3 squared, that's 9, plus the square of this one. This is 4 and this is 2. So the length here is 2 plus 4, that's square root of 13. And D2 can be found the same way. So it will be the square root of this length, which is minus 5 minus 2, that is 3. So that's 9. And the square of this length. This is 4 and this is minus 2. So 4 minus minus 2, that's 6 squared. That's 36. And this will be 45. R1, it should be square root. Okay, so the magnitude then will be R1 times R2 square root 32 times square root 17 divided by square root of 13 square root of 45. And if you calculate these, you should get 0.96. So this system will attenuate this frequency by 4%. Instead of amplitude 1, now it will be 0.96. And the same thing we can find graphically phi1, phi2, theta 2, and theta 1 without even plugging any values for SI, P1, P2. But if we want to plug values, then you will get the same answer. So if I plug, this is the same equation we started here with, and we factor it out here. So now if I plug for S, this specific frequency, I get this one minus 2, and here, and here, and for this one, same thing here. Then minus 2 is minus 4. I get this operation. I add here, I get this one. And the same thing for these denominators. I get these two terms, or these two vectors. Now, if I express this vector in polar form, it will be this. And this one, it will be this one, and so forth. Now, if I calculate the magnitude, I get 0.96, exactly what I got here. Let's summarize it. The magnitude response of the system to any frequency, let's call it P here, will be the product of the distance of zeros to P. So the distance here from this 0 and the distance here from this 0 divided by the product of the distances of poles to P. This distance D1 and this distance D2. That will be the magnitude response. Now, the phase response is the sum of zeros angles to point of interest. So this is the first zero angle, this is the second zero angle. You sum them up, you get this. If you have more than two zeros, minus the sum of poles angles to P, minus these is the poles, these two, minus theta 1 plus theta 2. And that would be the phase. In general, it doesn't matter how big is your system. Your system could be of n order. So h of s, you can factor out the numerator to find the zeros, and you factor out the denominator to find the poles. And sometimes, depend on the amplification, you may have a constant here if you need specific amplification. And then if you want to know what is the system response to a specific frequency, you plug for S, that frequency, and then each term here will be a vector. You can express it in polar form, magnitude, and phase. And then the system response magnitude will be R1 times R2 times all the way to Rn divided by D1 times D2 all the way to Dn. And that will be this one. And this is same thing, the phase response. So let's look at some examples, filter, low pass, high pass filter, and see how the placement shape the frequency response. In the previous examples, we did not put any conditions on the frequency. It could be a complex frequency. It has sigma and it has omega. That's a decay rate, that is oscillation rate. So that frequency could be anywhere here. And we found how the system responds to any one. But if I am interested only on sinusoidal with oscillation rate, that means sigma is 0, then all my point of interest or frequency of interest will be along this axis here. So it could be omega 1, omega 2, omega 3, omega 4, omega 5, and so forth. And the poles always going to be here at the negative, at the left hand side. Zeros can be anywhere. So now if I restrict S to be j omega along only this axis, then we call it the frequency response. And let's see, by placing certain poles and zero at certain locations, how these magnitude h of omega will be formed. Our first example, we have a simple second order system. It has two poles, and these are the two poles, here and here. and I want to know how the system responds to different frequency along these axes. Let's start with the magnitude. So let's start with the DC input. That means the frequency is 0 here. How the system gonna respond? The system response is the multiplication of distance between the zeros and the frequency of interest. We don't have any zeros in this system, no zeros, so that will be just 1. Divided by the product of the distances between the poles and the frequency of interest, D1 and D2. So for a DC, then this will be D2 and this is the D1. And the magnitude for a DC, that will be this, 1 over D1 times D2. Now, as the frequency increase, let's say to this point here, now D1 gets smaller. Yes, D2 get larger, but the decay rate of D1 is at a faster pace than D2. So 1 over D1, D2 become a little bit larger. It keep increase. The peak here will be when the frequency is here, because now D1 will be the smallest possible value. And D2 increase a little bit here. But when you multiply D1 times D2, this denominator will be small and everything here will be larger and you get a peak. Now, if the frequency of the input increase, let's say all the way to here, now the distance from this pole D1 become large and D2 will be even larger. So when you multiply D1 times D2, that's a big number. And 1 over a big number, you will get almost 0. So then it will start decay. So the higher the frequency, the system response will filter it out. And this is like a low pass filter. And that's the magnitude. Now let's look at the phase. How does it work? Well, for a DC, this is the vector and this is the another vector. So this will be theta 1, this will be theta 2, and they will be the same. Because remember, if that was minus 1 plus J3, this has to be the conjugate, minus 1 minus J3. So that angle here will be the same when the frequency is 0. So theta 1, let's assume minus 45. Then theta 2 here will be positive. See, this is minus because this is the horizontal. So that's a negative angle. This angle is above the horizontal line. So that's positive. 45, you get 0. And that's the 0 here. Now what happened when the frequency increase? Let's assume now the frequency at this point here. Now theta 1 gets smaller and theta 2 get larger. So theta 1 gets smaller and theta 2 increase. And at that frequency here, at that specific, which is this one here, if theta 1 is going down, which is a negative value, let's assume it goes to minus 30, and these now go up from 45 maybe to 60. So what do you get? Minus 30 plus 60, you get 30. And then you have this minus 30. So then this will be around minus 30. What happened when the frequency increase all the way to here, like infinity? Now D1 will be this one. So this will almost 90 degree. And D2 will almost 90 degree. And 90 plus 90, that's 180 times negative, that's negative 180, which is here. So as the frequency increase, the phase go to minus 180. Because I put a pole close to this frequency, the filter response to this frequency enhanced the sinusoidal that has this frequency. See that peak? So poles close to the frequency of interest will enhance the amplitude frequency response. That's rule 1. Now let's look at the zeros. If I want to suppress a frequency component, I put zeros close to it. So let's see how this works. Imagine I have a system equal this one. So it has a 0 at alpha plus j omega. Alpha could be a -2 or -3, so that's this one. And alpha minus j omega, and that's this one. So I have these two zeros. So there is no poles. So the denominator will be just 1. So the magnitude response will be just R1, R2. R1 is the distance from the 0 to the point of interest. R2 is the distance from the second 0 to the point of interest. Let's take the first scenario when we have a DC 0 frequency here. Again, R2 will be this one, R1 will be this one, and the system response will be just R1 times R2. Now, as the frequency increase from 0 and increase, let's say to that frequency. So now the system response will be this R1 times R2. So now R1 decrease at a higher rate. So it used to be this one and decrease until it's here. So it's decreasing at higher rate. So R1 times R2 gets smaller and smaller. The smallest it will be when that frequency become here, j omega 0. Then this R1 here will be the smallest. And R1 times R2 will be the smallest value. That will be this here. So this system, because you put a 0 next to this frequency, you suppressed this frequency from your input. Then as the frequency increase, then this will increase. Just imagine if I have a frequency way up here, then R1 will increase and R2 will even get larger. And R1 times R2 become very large. Okay, let's look at the phase. This should be positive. Phi1 plus Phi2. So let's take the first case scenario when you have this is DC, 0 frequency, then this will be R1 and this will be R2 and this angle will be exactly like this angle, except this is below the horizontal line, so it's negative. This is above positive. You add them up, you get 0, and that's the 0. Now, as the frequency increase, let's say to this point here, then theta 2 will increase positively, and theta 1 will decrease, less negative. So if in the beginning here, if it was here, and let's say this was like 45, negative 45, and this positive 45, you get 0. Now, when we are in this scenario, theta 2 increase more than 45. So let's say just it becomes 60. Then theta 1 here will decrease, less negative. So instead of minus 45, maybe it is minus 30. So when you add them up, 60 and minus 30, that is 30. So at that frequency here, omega, maybe it's here. Maybe you have like 30 degree. Now, if the frequency increase, let's say to infinity here, then these become almost 90 degree, and these become almost 90 degree, and 90 plus 90, that's 180. And that's what this one is. So now you can see by visualizing the location of the poles and zeros, you can quickly plot the magnitude and the phase of the system. So the rule: system suppress frequencies near a 0. System enhance frequency near a poles. Let's look at the simple low-pass filter. You have this transfer function, and if I want to find the magnitude, it will be, this is just a constant, whatever it is, it could be 100 or 20, divided by the distance from the pole to the frequency of interest. So if I have this system, then it has a pole at minus omega c, which is this one. So if I want to plot the magnitude, when it's a DC, that distance is just omega c. That distance d is just omega c. So that will be omega c over omega c, that's 1. So this is 1. Now as omega increase, this distance become larger and larger and larger. So that quantity become more than omega c, and the whole thing will approach zero. So it's gonna be like this. And that's a low pass filter, first order. Now, if I want to build an ideal low pass filter, something like this, it allows all frequency between 0 and the cutoff frequency omega c to pass without any attenuation. Any frequency above the cutoff frequency will be eliminated from the signal or from the input. Then I have to have a higher order filter. There are different designs, but the Butterworth filter, you specify the cutoff frequency, and let's say it is here, and that's minus omega c. Then you draw a semicircle with radius omega c, and you place your poles along this semicircle. This one in this 1, 2, 3, 4, 5, 6, 7. It has 7 poles, so that's 7th order. And it will act almost like an ideal. Because look, if I have this frequency 0, then it is 1 over d1, d2, all the way to d7. So that will be all this distance. Now, if I have the frequency gone up to here, look how this distance change. Those get smaller, but these get larger. These get smaller, these get larger. So the product of d1 times d2 all the way to d7 of the blue distances will be almost the same as the red. So that's give you this flat. Until the frequency is above the cutoff frequency somewhere here, then everything just go up. And the product 1 over d1 times d2 times d7 become extremely small, this. And it goes to 0. The higher the order, the closer your filter will be to the ideal case. And here is a plot of different order. This is the ideal. This is the first order filter, which is this one here, which is this. This is a second order. See, it come closer. It's flat more here, then it goes down faster. And this is 4th, 8th, and that's the 10th order. See, it's flat, more frequency flat, then sharply go down. Okay, so that's the low pass filter. Now let's look at the band pass filter. Now, if I need a band pass filter that looks like this, you can think of it as if it's a low pass filter, but instead of centered around 0, now it's centered around omega 0. When it was a low pass filter, we had a semicircle with center around 0, and then we place all the poles here. Now, if I want a band pass filter centered around omega 0, same analogy, but instead of this semicircle around 0, it will be around omega 0, the central frequency. So I go, what is my central frequency of the pass band region? I specify it here and here. Then it depends on the order of the system and how fast do I want these to go down. If I want it to go fast, then I have to have more poles, more than just 3. So this is a 6th order system because you have 3 poles here and you have 3 poles here. Now, if I want my filter to look more like this, then probably I need to increase 2 more poles here. And to see how it works, if it's a DC, all this distance very large. So 1 over D1, D2, you have 6 poles, D6 will be very large. So that will be like low value until the frequency comes here. Now when it comes here, these D1, D2 become very small. Yes, this is large, but that small will offset this. And you start gonna have like some flat value as long as you are in this region. The moment you get out of this region, now all distance from the poles to the frequency of interest will become very large. And then it decay back again. Now, how big should that circle be? That will depend on the low cutoff frequency and the high cutoff frequency. That will determine the radius of this semicircle. What if you have a filter like this? Let's assume you have a 0 here and a pole here. This is 2, this is -2. So it doesn't matter where is the frequency. If it's here or here or here or here. This is R1, this is D1. And the magnitude frequency response is just R1 divided by D1, so that's 1. And the same thing here, that frequency. It is still R1 same as D1 and these, and no matter what frequency, R1 always gonna be the same as D1, so the gain will always be 1, the frequency response. So if that is frequency, this is the frequency response. So what's the purpose of this system if it allows everything to pass? Let's look at the phase response of the system. Here, phi1 minus theta 1. So phi1 here is 180, theta is 0. 100, so that will be 180 minus 0, that's 180. Now, as the frequency increase, these get less, these get more. So these minus these give you less value. Until you are here, these even get less and these get more. So you get less value. Now, if the frequency become very, very large, this will almost be 90 and this will almost be 90. And 90 minus 90 is 0. And that's the phase response. So a filter like this, the magnitude will not be affected, but the delay will change. So higher frequency will be phase shifted less than low frequency. And there are applications where you want to modify the phase. Okay, let's look at the notch filter. The notch filter looks something like this. The magnitude, it allows everything pass except certain frequency. It blocks it. For example, you may have a speech and there is a tone in the speech, like a whistle, like and you want to eliminate that tone from the speech. Then you use a notch filter. So it will allow all frequency components of the speech to pass with no attenuation except that tone. That tone could be 1000 hertz. You want to filter it out. Then you build this kind of a notch filter. So how do I eliminate that frequency? I put a 0 where I want to eliminate. So if that frequency is 1000 times 2 pi, I put a 0 here. So the distance from this 0 to that frequency is 0. So you have now R1, R2 divided by D1, D2. So you are eliminating this frequency. What happened if the frequency is a DC here? Then the system response will be this distance R1 times this distance R2 divided by this distance D1, D2. So if I want to have this 1, then I have to have a pole as close as possible to this 0 along this semicircle. Why I need them to be close to each other? So this distance R1 and D1 to any frequency along these lines will be almost the same. So then this will give me always 1. So even when the frequency go really high here, then the distance D1 here will be the same as this almost R1. And the distance from this to that frequency will be almost the same as the distance to this frequency. And then this will always equal 1. And that's how we build a notch filter. The frequency I want to eliminate, I put a 0 on that frequency, and then I put adjacent. Now, how close this should be? It could be here, or it could be even closer. So that theta will determine. So if theta is closer to the 90 degree, then this will be close to it. And what is the advantage? If the pole is closer, that means the distance R1 and D1 will be very close to each other. So you will have flats for a long frequency range. Now let's say I have two tones of noise in my speech, one 1000, one 2000. So I want to eliminate this frequency and this, let's say, and they are in radians per second. Then we need to put a 0 here and a 0 here, and they have to have their conjugate, and then a pole. So if I draw a semicircle here, that will be the pole here, and this one here. And if I plot the magnitude, it will look something like this. This will be the 1000, and this will be the 2000. So that's how to visualize it graphically. But how if I want to find h of s? So the engineer can build the system and use it. Not difficult. As long as you located the zeros and the poles, then h of s is very simple to find. All you have to do, this is s minus j omega. So this is like s minus the first 0 times s minus the second 0. And you place the first 0 at j omega 0 and the second 0 at minus j omega 0. So you plug for z1, j omega 0, that will be this one. You plug for z2, minus j omega 0, that will be 1. You get these quantities. Same thing, I can express the denominator here as s minus pole 2, and this quantity will be s minus the first pole. And let's call this is the first pole, and this is the second pole. So if I want to find the coordinate of this pole, it's the projection of these along the x-axis. So this one will be, this is omega 0, so it will be omega 0 cosine theta. And along the vertical axis, it will be omega 0 sine theta. So pole 1, the real part is minus omega 0 cosine theta, and the imaginary part is plus j omega 0 sine theta. And the same thing here. I don't even have to do it because I know the second pole has to be the conjugate of this one. So the second pole has to be minus omega 0 cosine theta minus j omega 0 sine theta. And then I plug for P2, minus time minus, I get omega 0 cosine theta. Minus again, time minus, I get the j omega sine theta. And same thing here. If I multiply minus time this minus, I get plus omega 0 cosine theta. This minus time the plus, I get the minus j omega sine theta. And if you multiply these, you will get s squared plus omega 0 squared. And the same thing, if you multiply these vectors times this one, you will get this. And if it's given that you want to suppress a 60 hertz, then omega 0 is just 2 pi times 60. And if you square these, that is the number. Here, that will be this. And square this one, that's what you will get. And then you plug to omega 0, that's the number you will get. And here it's left in terms of theta. So it is up to you how close do you want the filter to pass higher frequency and lower frequency. The more you make theta close to the 90 degree, the faster it will grow. But if you have a noise that is not just pure tone, you have more noise here, a small theta will suppress more of this noise. But if you make theta like 85, it will suppress that point, but this noise will stay. So it depends on your application. You decide how much theta you want it to be. That ends our system design by using poles and zero locations. Thank you, and I will see you in next videos for the Fourier series and Fourier transform.